Okay, today we're going to be talking about the spectrum. Woohoo! So fun. Alright, so the reason why that there's a spectrum is because light acts like a wave. Light acts as a wave. Now, but you told me yesterday that light acts like a particle. Yes, it has behaviors of both. But what is it really? Good question. And we'll leave it at that. Alright, so what does it mean to act like a wave? Well, that means it acts like sound. Alright, so let's draw a picture of a wave. Beautiful. Okay. So there's a wave. Now there's some measurements that, words that we have to be familiar with here. One of the important ones is this distance right here. And this is wavelength. Alright, so wavelength is how far from crest to crest, or trough to trough, or middle to middle. Well, every other middle, but whatever. Alright, this is going to be in meters, or like how far as in a distance, okay? So that is light, right? That is wavelength of light. Now, usually for light, it's going to be in nanometers, right? Because light has a pretty small wavelength, so we use nanometers instead of normal meters. Now, if you don't remember, nano is 10 to the minus 9, okay? So, if it's like the typical wavelength of light could be like 500 nanometers, so that would be 500 times 10 to the minus 9, or 5 times 10 to the minus 7, but they always have it as minus 9 because it's the English system instead of the scientific system, which, in my opinion, is better, but they didn't ask me. So there's another one that's important, and that is frequency. Oh, I suppose we should write it. So this is how many waves pass in 1 second. Okay? So let's say we have this beautiful red wave here. It's going to the right. If you are standing here and the wave is going to the right, let's say this whole thing passed through, okay? What you see passes through. So that means there is one from here to here, that'd be one wave, here to here, a second wave, and then 3/4 of a wave. Okay, so there's definitely room for fractions here. So this frequency here would be, what was it, 1, 2, so 2.75. Okay, so that's how many waves pass through. Now, for the units for this guy, it's like waves per second, right? But there's no like real unit for waves, so we don't count that. So it's just 1/seconds. 1/second is a hertz. Yeah, I know, but hopefully it's not hurting you. So that is frequency. Okay, now the important thing, there's a very important formula here, the wave formula. The wave formula combines the frequency and the wavelength together. Wavelength is written as a lambda, right? Frequency is written as an f. Now, the reason is because wavelength is a distance, right? And we're going to multiply that by frequency. So wavelength is a distance, and we're going to multiply it by frequency, which is 1/seconds. You're going to get meters per second. So you are going to get the velocity of the wave, the speed of the wave, but we're all big boys here, so we'll say velocity. Because that'll tell you meters per second. Because this guy tells you how long each wave is, and this one tells you how many of those per second it is, so it comes out to speed. Alright? Remember, when you're doing this, though, you want this guy to be in meters, and this guy to be in, hertz, I guess. Sorry, not seconds. hertz because 1 over seconds. That way you'll get a meters per second speed instead of like a nanometers per second speed, which, I mean, I suppose it exists, but I've never seen it used before. Okay, but we're going to talk more about wavelength here, because this is how they typically categorize light, by wavelength rather than frequency. But, you know, it doesn't really matter because velocity is always going to be the same, right? Light is always going to travel at, get this, the speed of light. Right? Do you remember what the speed of light is? The speed of light is 3 times 10 to the 8 meters per second. Very fast. So, or, you know, 3.00 if you wanted to go there. Now, I know yesterday we told you it slows down when it passes through some different materials. Well, it's not by a lot, or at least not anything that you're going to have to worry about. So when it goes through air, it slows down by a couple million meters per second, but that's a drop in the bucket when you have 300 million. So, I'm sorry, a couple 100,000, whatever. It's going to be a constant pretty much for you. Okay, so let's talk about. There are lots of colors out there. You know your rainbow, hopefully. So here's a red color. And here's an orange color that's written in red. And here's a yellow color that's written in red. Green, blue, indigo, and violet. All right. So what they do is they categorize these colors by their different wavelengths. This is the range that you can see. So just so you have an idea, you're not going to have to memorize this number or anything, but red is going to be around 700 nanometers for a wavelength. And violet is going to be around 400 nanometers. So anything outside of that, your eyes just can't pick up because, you know, they're not built to take in those wavelengths. The photons just don't activate your eye receptors, which we're going to talk about later in the week. Okay? And everything else is between there. So green is like 500. Yellow is going to be a little more than that, like 600, or, well, I mean, it's 550. And these are not evenly distributed either. You will notice that red has a very large range, while yellow seems to get smushed really close in between orange and green. But a story for another day. Now, we're going to be focusing mostly on visible light here because we're trying to approach it from, you know, a useful point of view. But there's nothing special about stopping at violet. This range does go on. Okay, so after violet, you have not just any violet, but ultraviolet. Alright, so this is if you continue, so this will have an even lower wavelength. Past ultraviolet, you have X-rays, and past X-rays, you have gamma rays. Delightful things those are. Okay. After red, you have infrared. You know, this is the other side now. After infrared, you have radio waves. And I'm going to put a slash here, and I'm going to put microwaves. This is where microwaves are too. Now, the borders between these, especially the radio and microwaves, is kind of fuzzy. So when does infrared stop and when does radio start? It doesn't really matter because, you know, it's a continuous thing. So light could be, you know, at 700 and it can be at 699. Is it less red? I mean, technically, when does it become orange? That's more of a subjective thing, but the measurement of the wavelength, that's something you can get absolutely. So something you should notice here is this has a big wavelength, this has a small wavelength. So the wavelength is going to go up when you go to the left. Okay, let's talk about energy. Which ones of these have the most energy? Well, the energy is going to go up when you go to the right. The reason is because these guys, right? Just think about what you know. These guys are the ones you want to watch out for, your ultraviolet rays. The reason why they're bad for you is because they go through your skin. They go through your skin, cleave your DNA, and then your body puts them back together wrong, and you got cancer or something like that. X-rays go through more than just your skin. They go through all your soft tissue. That's why the doctors use them to see if your bones are broken, because only the tough bones in your body don't allow X-rays through. Gamma rays are used in MRI machines because they can look through your bones to see, brain scan type stuff, because it can go through your skull. So these are the different types of rays. They have the more energy on the right, less energy on the left. Okay, so we're going to talk about how you perceive them another day, but this is the different flavors of these waves. All right, now there is a formula for energy as well that we're going to need to know at some point. You should be aware of it anyways. All right, so energy is going to equal H times F. Wonderful. So energy is here. Energy is going to be measured in joules. Do you remember joules from back in the day? If not, we'll remind you right now. This guy is your old friend frequency, which is in hertz. And this guy is a constant. This is a Planck's constant. I don't think there's a C. My bad, Planck. Alright, now because it's a constant, it's just a number. It's the same number every day of your life. It is going to be 6.628 times 10 to the minus 34. And that has a unit of joules seconds. Why is it joules seconds? Because when you multiply by frequency, remember frequency is 1 over seconds, the seconds cancels out, and you're left with joules. Ta-da! So that is Planck's constant. It is a very small number because photons have very little energy. I mean, by themselves. When you walk outside, you're going to be pelted with billions of them, but that's not important right now because who goes outside anymore? So this is your formula for calculating energy. Ta-da! We're going to have fun doing stuff like this on your homework. Good luck!